see the transformation diagram for this. And in the transformation diagram, we talked about the basically formation of ferrite and cementite in a laminar structure which we call as pearlite formation. Austenite is transformed to pearlite. The mechanism involves the diffusion of carbon over some distance, which is the interlaminar spacing between the middle of the ferrite plate to the middle of the cementite plate. When the temperature is lowered further for transformation, that's physiology faster cooling, the diffusion is becoming difficult for carbon, and then the transformation to bainite occurs because the driving force for FCC austenite to go to BCC ferrite is very high. So by some mechanism it wants to go to become BCC, and that's what we showed you last class, how the FCC can become BCC. Actually it becomes BCT, and if the carbon is not present, there is enough contraction along the C axis, it becomes a BCC. Then if we further cool it at a still faster rate, so the transformation takes place at a much lower temperature, somewhere around room temperature, then even bainite cannot form because this involves the diffusion of carbon. Martensite is formed which does not involve any diffusion of carbon. And that's what we have begun to look at in the last class.
So bainite is also a mixture of cementite and pearlite?
Yes, not pearlite, cementite and ferrite, but that cementite I told you is not an equilibrium cementite Fe3C. Similarly, the ferrite is not the equilibrium ferrite because they have not got enough time for carbon to diffuse to longer distances.
Means that 0.02% composition of ferrite
May be different. It could be different from there. Yeah, it is not in equilibrium.
and what in the case of martensite?
There's no carbon is diffusing out. We'll just they're talking about that only today. Well, this picture of annealing where we do a very slow cooling and it's possible to form a coarse pearlite like this. A coarse pearlite is formed in this temperature range. And when we do this cooling, a fast cooling in air instead of in the furnace, fine pearlite is formed. Because the nucleation rate is much higher. Here, so very fine pearlite is formed. And then we saw that if we hold it isothermally below the nozzle seeker, that I refer to as the process of austempering, but bainite is formed. Of course, you know this is your temperature axis and this is your time axis.
So it should come below the nose of the seeker.
That's right. Otherwise, here the mechanism for pearlite begins here, bainite cannot start. Once the mechanism for pearlite has started, the cementite has nucleated. In between, the region will become ferrite because of the diffusion of carbon. Only thing is, these are finely spaced. So once one mechanism begins, the other mechanism cannot start. That's important to understand here. Right. Now we are looking at the yeast transformation. When I cool it still faster, I don't hold it isothermally, just simply take it down to the room temperature. Well, this martensite, which is body centered tetragonal in shape, all the carbon remaining in solution, see that 0.8% carbon was in solution in FCC, that remains in FCC. That's what is formed. this is your temperature of 725 degrees centigrade for this Eutectoid steel. This time here is 1 second. This temperature I said is around 270 degrees centigrade, and that may be around 120 degrees centigrade for this steel. We quench it rapidly like this. I am not going close to the nozzle seeker, not touching it, not crossing it, to form the martensite. Martensite begins to form at this temperature, which is 270, and finishes at this temperature. By the time it reaches room temperature, it's already formed martensite. And in this region, I have both austenite and martensite, while I have here only martensite. So here we are not providing enough time for carbon to diffuse. Temperature where the diffusion is required to take place is very low, and carbon is unable to diffuse. Even though it is an interstitial mechanism of diffusion, it's a very slow process, it cannot take place. And therefore this deformation, this transformation is brought about, as I told in last class, by a deformation mechanism, which is called a shear mechanism. Well, if I consider this to be the c-axis for the martensite, this is the, let's say, A1 axis, and that's the A2 axis. And if you want to name your FCC lattice, you can call this as the B axis and that as the A axis. C remains C. Only thing is the phase diagonals of the FCC become the A axis of the B axis of the A1 and A2 axis of the BCT matrix or the BCT lattice. And here, as I said, I require contraction along these axes to the tune of 20%, and I require extension along A1 and A2 to the tune of 12 to 13%. This contraction here is 20%. If the carbon is sitting here, then it does not allow this to go down by 20%. It is not reduced by 20%. It reduces by less. So I get some capability left in the matrix. As I said, C by A is equal to 1 when carbon is 0, pure iron, and this is equal to 1.08 when carbon is about 1.2%. And no carbon is able to go out, the matrix is transformed, and it has become the martensite. But this kind of transformation does not take place simultaneously all over the volume, and particles form either in the form of lath or they form in the form of plates. Plates are lenticular in shape and they cannot fill the whole space, while lath has a tendency to fill the space while the plates do not have. So, as compared to the classical transformation of austenite becoming ferrite and cementite, what I call pearlite, or another structure, another morphology of bainite, where carbon is diffusing, compared to that, there is no change in composition in this transformation. 0.8% carbon remains 0.8% in the matrix.
So then how will we distinguish? It is also 0.8% and this is, we say that transformation is occurred when some compositional differences.
Not necessarily. Transformation can take place when there is a change of composition, when there is no change of composition. When water freezes at 0 degrees centigrade, what is the change in composition? No, the transformation has taken place. Water has become ice.
There is a single component.
Yeah, that's what it is. So there is no change in composition. It can also give rise to a transformation. There is a change in the crystal structure. FCC has become body centered patternal. There is a change in structure. Properties are vastly different. And there is a change in crystal structure. There is no change in composition, but there is a change in crystal structure. The transformation is brought about by a diffusion loss mechanism. There is no diffusion of any atom, iron or carbon. Iron there is no question because vacancy mechanism is a very slow process. Interstitial mechanism, which is a faster process, even that is not able to take place at room temperature. And the transformation is brought about by the shear deformation, therefore it is a function of the driving force and not that of the time. Because diffusion is not involved. Driving force is decrease in the free energy. For any process, any transformation, the driving force is a decrease in the free energy. Since I have come from 725 degrees centigrade where there is an equilibrium, free energy change there is zero, come to a lower temperature, the free energy change will be very, very high. And that's what it is. So as particular temperature, there is some driving force, more undercooling, there is a more driving force, still more undercooling, still more driving force. So it's a function of temperature and not that of time of holding at that temperature where diffusion is not involved. The mechanism is the shear deformation as I explained. Along the two axes there is an extension, third axis there is a contraction. And the shape change that involves gives rise to large strains and therefore there is a considerable strain energy involved in the process. Driving force is going to provide that strain energy. Besides the shape change, there is also a change in volume involved. The matrix expands by about 4 to 5% when there is a transformation from FCC to BCT or formation of martensite. This 4 to 5% expansion, if it is taking place in the whole volume, there is no problem. But it's not taking place in the whole volume. Where the plate forms or where the lathe forms, there is an expansion. Where it doesn't form, there is no expansion. At the same time, what is happening is when I quench from here, surface of the steel is cooling at this rate. The interior of the steel will not cool at this rate. If I want to transform the interior also to martensite, interior should also be fast enough not to cross the nozzle C curve. So this is the exterior of the steel and this is probably the center of the steel. Then I am sure that it's going to be all martensite. Even then, plate cannot fill the whole volume, so there is a retained austenite. Plate is a lenticular shape, it cannot fill the space. Laths, which are the shape of a ruler, they can fill the whole space. So if we get about 100% or 99% martensite, it is when it is in the lathe shape. When it's a plate shape, we don't get that much martensite. So interior must also cool rapid enough not to cross the nozzle C curve. If it crosses the nozzle C curve, then interior is forming pearlite and the exterior of the surface is forming martensite. Second thing is, at any given time, let us say I talk about this time. At this time, this is the temperature in the center and this is the temperature, this is the temperature in the surface. Surface has become martensite, the interior is still austenite. This This is also in this temperature it is austenite. Only in this temperatures some part of it has become austenite, the surface. The transformation is also not uniformly same given time. Some part is transforming, some part is not transforming. Some place there is an expansion, other place there is no expansion. In other words, when the temperature is different, thermal contraction. It's because I am cooling it. I am not talking about expansion, I am talking about thermal contraction. Surface layers are cooling, therefore they are contracting more. Interior is not cooling, interior is not contracting. In other words, what I am trying to tell you is there is a differential expansion and contraction taking place, which is not uniform all over the volume. As a result, there are large residual stresses developed in the material, which sometimes can become so high that there is a cracking of the steel. They give you a plain carbon steel, ask you to austenitize it and quench it in water, invariably you will crack it. It will crack because of these large residual stresses which are developed, and the material becomes brittle. Cracks are the one responsible for making the material brittle, and therefore our intention is to make it, if possible, ductile. In here I show the hardness of martensite. This is not a very smooth curve because I have taken the data and plotted this, the experimental data. The hardness, which is also a measure of the strength of the material, is a function of the carbon content in the steel. At about 0.6% carbon, it reaches probably a high value of about 63 or 65, around somewhere there. Okay? What's the hardness you reach at about 0.6% carbon? At less than 0.6% carbon, the hardness is decreasing with decreasing carbon. At that point, steel is very, very brittle, but here, as I lower the amount of carbon, hardness decreases, steel may not be very brittle. But the hardness is also not very high. Strength is not going to be that much. So if my intention is to make the steel hard by transforming it to martensite, then I must have 0.6% carbon. And this is irrespective of whether what allied additions are available in the steel. It's a function of carbon. The hardness of martensite is a function of carbon. Now, in this table, I'll show you the hardness as well as how is it related to the strength, which is the tensile strength we call it. I'll explain what the tensile strength and the yield strength and other things are when I come to the mechanical properties. The tensile strength is related to the hardness. That's what I'm shown here. As the hardness increases, the tensile strength also increases. And the second thing which I'm showing here is the coarse pearlite, where the distances between ferrite plate and cemented plate are larger. That's the thickness of the ferrite plate and whereas the cemented plate is large enough. The hardness is small, it's a very soft material, but the strength is also less, 710 megapascal. But when it is cooled in air, normalized, fine pearlite, the distances between the thicknesses of the ferrite plate and cemented plate are smaller. Hardness is 30 while the strength is 990 megapascal, almost 1000. When I form bainite, there is still more finer distribution of carbide. Its hardness is 45 and tensile strength is 1470 megapascal. But in martensite, it is 65, as I told you, for 0.6% and becomes around there. So at 0.8, it is same value, 65. But the tensile strength, I am not able to measure because it falls within its elastic limit. It doesn't even reach the yield strength, it's a brittle material. That's what I want to get rid of. For that, we temper the martensite by, after transforming the steel to martensite by quenching, we keep it in elevated temperature. It could be anywhere above room temperature up to about 400 degrees centigrade. And thereby I try to gain some ductility in the steel so I can measure some tensile strength of the steel. And there's some plastic definition in it, but I have to compromise and lose some hardness. 65 it goes to 55. That's not my intention. By tempering I don't want to reduce the hardness, that's not my intention. The hardness I wanted to achieve and is to make the steel stronger. But it became better, so to gain ductility I do the tempering and I gain the ductility, I get the tensile strength, but I lose some hardness. That's a bargain. Okay? But that's not the intention of tempering. Let's see what happens during tempering. Martensite is very hard and brittle, as I already told you, and it cannot be put to use without gaining some ductility. And in order to gain that ductility, as I said, we do the tempering of the steel. The process of tempering causes a martensite, which is a BCT structure. When I heat it, tempering means keeping an elevated temperature, above room temperature, usually maybe 200 degrees centigrade, 250 degrees centigrade. But more the temperature, we will be losing more hardness. The process will be much faster because it's a process involving diffusion. Where all the carbon is in solution, martensite, I would say that. It's all in solution, all the carbon. And this carbon goes to form, diffuse out, become ferrite and cementite. The structure which forms now is not pearlite. Pearlite is a name given to a morphology where ferrite and cementite plates are alternately arranged. If you temper the martensite, what you will get is spherical carbide or cementite embedded in the matrix of ferrite, like this. This morphology of spherical cementite is not called pearlite. Right? Similarly, dynamite, what we call, is not like this. There are plates or lats, in between we have the martensite needles inside the plates, and where in between the lats we have some carbide coming out. Right? So this is what the structure forms. Is altogether a different structure. This is not called pearlite. That's the ultimate thing, but that if that goes to this stage, it's a very soft steel. You have lost all hardness. It is softer than the coarse pearlite. Softest variety of steel is this, where cementite is spherical in nature, and it's called spheroidized steel. Okay, so this is the softest form of steel we have. That's the distillation of cementite in ferrite matrix gives rise to a very soft, where the cementite is in spherical shape, gives rise to a very soft steel. But intention of tempering is not to make it soft, but to gain some ductility. And as I said, hardness decreases is a bargain. I have to compromise on that. So this process, since it is going on at a lower temperature, it's possible for you to control the time and therefore the extent of the process. If you keep it for a certain time, just bring it back to a low temperature, room temperature, you are able to use it, the further tampering will not be there. And you have stopped the process of diffusion of carbon.
The extent of tempering can be controlled.
Can be controlled. Because it's happening at a lower temperature. Lower temperature is in the lower branch of the TTT diagram. And when we are in the lower branch of the TTT diagram, the diffusion is slow. It's going to take time. You can control time.
So then we can control the amount of ductility we want.
Yes, exactly. You can gain the ductility, and more the ductility you want, more the hardness you have to lose. That's of course you have to compromise there, right? As I already said. So very ductile, very soft, but hardness is not there anymore. So you have to stop this process of tempering as we desire, depending on the hardness hardness I need. So here now my process involves the diffusion of carbon, because all the carbon which is in solution in martensite has to come out in the form of carbide. And by manipulating the time and temperature, I can control the extent to the extent I need it. And it's possible for us to do it very, very accurately, because the role of temperature is more than that of the time. Okay? That's time comes the logarithmic form, but the temperature is linear, so therefore the role of temperature is much greater, and the control can be made very accurately. So for example, I was to make a chisel from the steel. I took it to austenite temperature, quench it to make it martensite. But chisel, how the chisel is going to be? Hard is needed because I want to cut something with the chisel. I want some hardness, right? So we have hardened it. But now when I use the chisel, I have to hammer it. Keep on something so that it cuts, that edge cuts the object, which is softer than this. And when I hammer, I am applying some impact. Brittle materials cannot withstand the impact. So my chisel is in brittle, it will not withstand. So I need some lot of ductility in it. So I temper it to a little higher temperature to a greater extent, because I need this chisel to be ductile, so it can take the impact. Right? Same way, if I have a hacksaw blade where I have to be cutting, I am not impacting it. It can be very hard, because I need the hard edge is required for cutting operation, because the hard material can only cut the softer material. Right? So I need the hardness. I would not temper it to that high extent as I would do it for chisel. Chisel, I will gain more ductility rather than the hacksaw blade. Right? Like that, we have to control the hardness and ductility in the material. Well, that's what I was trying to tell you. Quenching introduces residual stresses in the steel. And the reasons I gave you were, one is the thermal contraction, and second one is the transformation of the matrix, which again is not uniform. It is not the whole volume. Part of the volume is transforming. And that's what residual stresses lead to the cracking of the steel. And I asked you, but if you take any plain carbon steel, quench it from the austenite temperature, invariably it will crack in water if you quench it. However, we may stop this cracking if you can do it in a slower process like dropping it in oil. Maybe you can stop cracking. Now, how to overcome this problem is very essential for us. It's a very serious problem. For this, we would like to make the steel more hardenable. What is the hardenability of a steel? Hardenability is not the hardness of the steel. Hardness of the steel, martensite particularly, I told you, is a function of carbon. If carbon is 0.6% or more, it is 65 RC. If it is less, it will be less. So hardness is different from hardenability. Hardenability is the ability of the steel to harden by transforming to martensite without resorting to drastic quenching. What is the meaning of that? If I do not do the drastic quenching, I am doing slow cooling. Obviously, little slow cooling. So that the surface and the interior, there is not large temperature gradient. Heat from the center has come to the surface and taken away by the quenching medium. Right? That heat is being taken away, and the temperature difference between the exterior and the interior is not there. As As a matter of fact, the ideal situation would be interior and exterior steel both at the same temperature. There will be no differential contraction taking place. Right? So therefore, for better hardenability, therefore we have said that there should be no drastic quenching. And then when the temperature on the surface and the interior is the same, transformation will also take place in the interior as well as in the surface. It will form martensite. So I am not only reducing the strains due to the thermal contraction, I am also allowing the steel to transform interior as well as exterior to martensite. When the temperature is same, right? When the temperature gradient is there, surface is becoming martensite, interior is not. That is what I am trying to avoid. So that's why I said no drastic quenching, then it should become martensite. This requires the process of a slow cooling. Therefore, the bay, which is at the nose of the sea curve, must have a high time. Like 1 second is too small for 0.8% carbon steel. Right? For this reason, we add some alloying elements to the steel, which are substitutional alloying elements, and they give rise to shifting of the nose of the TTT diagram to higher time. Higher time means to the right. That's what is shown here. This is the 0.8% plain carbon steel. And this is the alloy steel. The 0.8% carbon. But it has alloying additions like manganese, nickel, vanadium, and so on and so forth. This time, as was already said, is about 1 second. Here I'll show you this time is 10 seconds. As for the Pearlite nose, the Pearlite nose, if you look at, time would be in the range of an hour.
Can you show in this diagram how can we achieve the transformation martensitic transformation without resorting to quenching? How can we achieve? We have to rapidly cool.
I know. Plastic, it should be. See, the question is rate of cooling here. If it is 140 degrees per second, it should be here less than 50 degrees per second. This quenching, what will be the quenching? The rate of cooling has become slower. Right? Another thing, when I have so much time available to me, what I can do is, let's say my surface is cooling like this, interior is cooling like this, okay? If there's enough time for me, I can hold it for a while. So the interior and exterior both are the same temperature. And then I quench it. Further, that I also can do. So why do I have enough time here? I'm able to cool it such that I can do not cross this or do not cross that. Okay? I have equilibrated my temperature and then I can quench it. So the exterior and interior are trying to transform simultaneously. It's not happening that the surface becomes martensite, interior is still soft austenite. Alright? So this is what the alloying additions are doing. They are shifting the nose to the right. Now binary nose is at 10 seconds, this is at about an hour for an alloy steel. Depending on what alloying additions I make, this can go still further, it can not go that much. It all depends on the alloying elements, whatever alloying elements present. Well, there is only one element which is an exception. That's cobalt. If cobalt is added, time doesn't shift at all, don't ask me why. Okay? That's the only exception. All alloying additions shift the nose to the right so that we have more time, more hardenability of the steel. So hardenability, the way it is defined, resolves to the fact that I should have more time here at the nose. That's what I am interested in, more time. So that I can still form martensite and I don't have to do the very fast cooling, very drastic quenching rather. So I don't have to do that. Rate of cooling can be low. Well, you can see that if this nose, my gas is about 350, let us say, and this is 725, this temperature is about 400, let us say, and I am cooling in 10 seconds, it's 40 degrees per second. The rate of cooling I require. Well, here I might need about 130 or 135 degrees per second. That's the way the rate of cooling is reduced. Alright, this is one of the functions of the alloying additions made to the steels, that they provide better hardenability to the steel by shifting the nose to the right. Okay. The second function of the alloying additions is they reflect on the tempering. When the alloying additions are present, particularly like chromium, tungsten, molybdenum, etc., the secondary hardening takes place in steel. During tempering, this is the temperature of, this is the hardness. And here is the temperature of tempering. This is the iron 0.8% carbon steel. Hardness decreases depending upon my temperature. Time, as I said, is not very effective, but let us say I have done it constantly for all of them for 10 minutes. Held it here for 10 minutes, held it here for 10 minutes, and the hardness is decreasing. It decreases very rapidly beyond 400 degrees centigrade. But when the alloying additions are present, I get another, not only decrease due to the tempering process, but there is an increase because of the formation of very fine carbide. Which I call precipitation process. Carbide is coming out from the mat as a second phase. Not always the second phase which comes out gives rise to precipitation. It comes out much faster and much than it's not precipitation. When it's very fine, it's coming, carbons diffusing slowly, carbons are forming, precipitation takes place, and that gives rise to increase in hardness. And as a result, you started with this hardness, and you have almost the same hardness after tempering. You're at 450 degrees centigrade. So you have gained lot of ductility. You have reduced all the stresses, but at the same time your hardness is not lost. So alloying additions are doing this also. The substitution alloying elements which are present in the steels. I said the steels you have thousands of varieties already available. Compositions, and then what treatment do I give it to? I do it, and I anneal the steel, I normalize the steel, or harden the steel, temper the steel. What all processes I am letting the steel go through, my properties of the steel will depend upon. Because microstructure is what I am controlling by doing all these things. Right? And it is happening because Eutectoid transformation is there on cool while I cool the austenite to a lower temperature. This secondary hardening, which is caused by the precipitation of fine alloy carbides, is what we shall look at the next, the process of precipitation itself. For I'm looking at the precipitation, the process I use an alloy which is non-ferrous alloy, is an aluminum copper alloy. And this is of course the temperature aluminum copper diagram. Part of the diagram I'm showing, that's around 4.5%. Copper. It's a eutectic reaction. Theta phase has about 52 to 54% copper. The alloy which we use for discussion of the precipitation is duralumin. Duralumin contains aluminum and basically 4% copper. Usually there are some additions of titanium like 0.5%. We'll not worry about that because we look at the binary diagram. Well, let's say I take an alloy with 4% copper. I am somewhere here. This temperature is around 550 degrees centigrade. It's all alpha here. Single phase alpha. If I cool this alloy slowly, when I cross the solvus line, there shall be theta phase begin to form. And as I cool more and more theta phase will form. That will be given by this lever, this fulcrum, and this is the fraction of the theta phase will be this. If I do slow cooling, second phase will form like this. But what we do is, we take it from here, when it is all single phase alpha, quench it in water or bring it to below room temperature. So I have not allowed any copper atoms to diffuse out of the matrix. Everything remains in solution again. Right? Now at room temperature, as the time progresses, the theta phase shall begin to precipitate out, and it forms in the form of small particles. Now mind it that the supersaturated solid solution goes to saturated solid solution and precipitate. That's the ultimate thing which will happen, and that's how the precipitation reaction can be written. When I am talking about this, I am working at the TTT diagram, the lower branch of the TTT diagram below the nose of the C curve. I am not working above. In the case of Austenite going to Pearlite, we are working in the branch which is above the nose of the C curve at high temperature. Now I am working at a temperature which is much lower because I already quenched from there to room temperature or sub-zero temperature. Now at room temperature, I am allowing the precipitation process to go on. Okay? Now, so far I told you that fine-grained materials have better mechanical properties. Secondly, I said if the solute is present, it increases the strength of the matrix. Like in the martensite, it's hard because all the solute is present in the solution. All these things I have to explain when I come to the mechanical behavior. Today I tell you, third thing, that if the interparticle spacing in the precipitate is smaller, higher is the strength of the material. Right? So the precipitate which is forming in the matrix or a given volume is solid, the large number of particles formed, interparticle spacing will be small. But from a few particles formed, they are big in volume, each one, the interparticle spacing will be large. So finally the precipitate I form, smaller will be the distance between the particles and therefore larger will be the strength. This is what you have to understand. I shall explain this, how it happens when I come to the mechanical properties. Now for this reaction to take place, the necessary condition is to have the reactant, to have supersaturated solid solution. How can you have the supersaturated solid solution? I gave you an example. Aluminum 4% copper alloy, around 550 you make it uniformly solid solution where it is not even saturated. But when you quench it, you make it supersaturated because so much of copper cannot remain in solution. At room temperature is only about 0.5% copper which is in solution. The rest of it is all making it supersaturated. Right? So, I can get the supersaturated solid solution by quenching, provided the solubility decreasing in decreasing temperature. Right? The solubility is not decreasing with decreasing temperature. Say for example, copper zinc alloy with alpha phase field. I don't make most of our rest of the diagram, don't worry about that. If I take it here, it's a solid solution. If I quench it, it's still a solid solution. It's not becoming supersaturated. I'm not going to do that. But if I take something like here, maybe you can heat it rapidly, here it becomes supersaturated. But how long will it stay? To have the temperature faster than diffusion. It will not stay there, so supersaturated, for any length of time. I want a supersaturated solid solution which is stay. Should be going towards the saturation at a very, very slow rate. Then only I get the aging process. The time is large. Right? Solubility must decrease with decreasing temperature. The sufficient condition I shall leave out today after I have explained what causes the aging process, precipitation, and giving rise to increase in strength. Then we shall try to understand what is the sufficient condition. But today only the necessary condition that solubility must decrease with decreasing temperature. Now this is what I was trying to tell you, that these are the rates here. This is the time temperature. This one is the growth rate, and that's the nucleation rate. And that's the equilibrium temperature. That's the temperature on the service line. And they have quenched it, lower temperature, and we are working in this region, temperature region. So as the temperature rises, nucleation rate increases, but the growth rate is smaller than the nucleation rate. And growth rate also increases with increasing temperature. But over time, growth rate is smaller than the nucleation rate. I'm not in this branch. I'm in this branch. I'm working at very low nucleation rates. I'm working at very low growth rates. And if I increase the temperature, the nucleation rate increase, growth rate increase. Right? That's what is happening. So, if I am working at this temperature, let us say, some particles nucleate, but they are unable to grow. With time elapses, some more particles will nucleate. And slower like that, some more particles will nucleate with time. As more and more particles nucleate, right, the interparticle spacing is becoming smaller and smaller and smaller. More particles are forming. But I cannot fill the whole volume, isn't it? It cannot become 100% because whatever is given by the delivery. If it is 5% or 2% or 3% of the volume has to become the precipitate, only that much will become. The remaining has to remain the matrix. That's what the equilibrium is. It's going towards equilibrium. But the rate of process is so slow and nucleation is so slow rate, I got very fine pressure particles, but they are unable to grow. So I get fine precipitate. And as the time progresses, more and more precipitate I get, so more and more means the decrease in the interparticle spacing is more and more, so the strength, the hardness increases more and more with time. While this process is also called age hardening. As the time or the alloy kept at room temperature increases, its hardness increases. Right? That's what it is. But this is the hardness and this is the time. Usually the logarithmic of time scale we use. This is at room temperature. It keeps on and on. Maybe this is already a few years. But at about 80 degrees centigrade, it is faster. The maximum is reached in less time, less than a year. And this is at about 200 degrees centigrade. This is reached in a few hours. What you notice here, as I said, as the time progresses, more and more particles are nucleating, hardness keeps on increasing. The interparticle spacing is decreasing. But let's look at this one, which passes through a maximum. Because this will also pass through a maximum, but that may be after 15 years or so. If it passes through a maximum at 18 degrees centigrade here, why is it passing through a maximum? Whatever volume fraction of the precipitate has to form as given by the lever rule has formed. No more nucleation will be possible after that. No more particles will be forming. So you reach the maximum. Beyond that, what happens is, I have created, because of a large number of precipitate particles, a large interfacial area. And interfacial area increases, provides extra energy to the material. Tendency is to decrease that interfacial area. That happens when the particles grow in size. So some neighboring particles dissolve and one particle goes. That's what is happening. Coarsening of the precipitate occurs here. And this is also called overaging. This is called optimum aging. After optimum aging, when the overaging is taking place, fractional volume of the precipitate is not going to change. But here the fractional volume is changing. Because total amount of precipitate, equal amount, has not yet formed. Keeps on forming. Now, second thing, at higher temperature, the initial hardness is higher. Because in the same time, more particles nucleate. Nucleation rate is higher. Okay? Second thing, the hardness maximum at the optimum which is there is lower at higher temperature. Because particles are also growing to a greater extent. Growth rate is also higher. So lesser particles are able to give me optimum hardening. And here no particles are required. Here still no particles are required. Because they are not growing. So if you understand that, we are in the lower branch of the nucleation rate and the growth rate. You will understand this. That's important. That's why it is called the process of aging. So the process up to the optimum, it is under aging. This is optimum and this is overaging, coarsening stage.